All right, today we're talking about something amazing, an incredible, invisible force that literally keeps our entire modern world from grinding to a screeching halt. It's a secret that's at work inside almost every complex machine you can think of. Seriously, without it, our society would seize up in seconds. So, here's a question for you. Have you ever really thought about how the metal parts in your car's engine, spinning thousands of times a minute, don't just weld themselves together from all that heat and friction? Or how a massive turbine that weighs tons can spin so effortlessly to generate our electricity? See, friction is the universal bad guy for every machine. So, how on earth do we defeat it? Well, the answer is this fascinating bit of physics called hydrodynamic lubrication. The main idea is just so simple, but it's absolutely brilliant. You engineer a situation where the moving metal surfaces, well, they never actually touch each other, ever. They are completely separated by a super thin, highly pressurized film of fluid, like oil or sometimes even just air. Okay, so how is this even possible? How does a simple fluid like oil generate enough force to lift tons of metal and keep everything perfectly separated? That's what we're going to get into right now. Let's pull back the curtain on this amazing phenomenon. The principle behind all this is surprisingly elegant, really. It all boils down to some basic ideas from fluid mechanics. And to get our heads around it, all we need to do is look at two really simple scenarios. And that brings us to the hero of our story, what I like to call the magic wedge. This incredibly simple geometric shape, this is the secret ingredient that turns a normal liquid into an almost impossibly strong surface. First off, picture two perfectly flat parallel plates, right? And there's some lubricant between them. If that top plate starts to slide, the fluid, it just gets dragged along. It moves, sure, but it doesn't build up any upward pressure. There's zero lift. If there's any weight on it, those plates are going to scrape together. Not good. But now, watch this. If we just tilt one of those plates, even by a teeny tiny amount, everything changes. The whole physical situation is completely different. This one little tweak is where all the magic starts. And this shape, this tiny gap that gets smaller and smaller as the fluid flows into it, that's what we call a converging wedge. And believe it or not, this simple little shape is the entire secret. This is how you generate massive lifting force from just a simple fluid. So, what makes this wedge so powerful? How does it actually create lift? Well, it all comes down to one thing: pressure. As that top surface moves, it's basically dragging fluid into that narrowing gap. The fluid gets squeezed, right? It can't get out of the way fast enough, so it's forced to pile up. And this pileup creates a huge spike in pressure. You can see it here in that arc from L to N to M. All that pressure pushes back, creating an incredibly powerful lifting force that fights against the load, which is marked as WZ here. To put it as simply as possible, as our source material says, the entire weight, all of that load, isn't being supported by the metal parts at all. It's being carried completely by the pressure that's generated inside that thin film of fluid. The parts are literally floating on oil. So now that we get the basic principle, let's take a quick look at the engineer's toolkit. It turns out there are a few different ways to use this fluid pressure, and each one is perfect for a different kind of job. First up, you've got your classic hydrodynamic lubrication. This is exactly what we've been looking at. The motion of the parts itself is what creates the wedge and generates all the pressure. This is perfect for anything that's in constant, high-speed motion, like the crankshaft spinning around in your car's engine. Then you've got something called squeeze film lubrication. This is for situations where parts are moving towards each other, in an oscillating or a start-stop kind of motion. As they come together, the fluid gets squeezed out from between them, and its resistance to being squeezed creates this temporary high-pressure cushion. That's the squeeze film doing its job. And finally, there's hydrostatic lubrication. This is the real heavy hitter. For truly immense, slow-moving loads, we're talking giant telescopes or massive bridge bearings, you don't even rely on motion. Instead, you use an external pump to actively force high-pressure fluid right into the gap, lifting the whole load before it even starts moving. So we have the theory, and we've got the methods, but how do you actually go from this beautiful, elegant physics to building a real-world machine that's going to work perfectly for decades? How do you turn this into precision engineering? That really is the million-dollar question, isn't it? How do engineers know the exact shape to make the wedge?
or how thick the oil needs to be, or exactly how much load it can handle. Obviously, they can't just guess.
They do it with an incredibly powerful mathematical tool, the Reynolds equation. Now, okay, I know this looks super complex, and trust me, it is. We are definitely not going to try and solve it right here. But what's really important is just to understand what it does. This equation is basically the master blueprint. It connects the pressure in the fluid to the shape of the surfaces, the speed they're moving, and the type of fluid you're using. So by solving this equation, engineers can predict exactly how a bearing will perform and design it perfectly for whatever job it needs to do. It really is the master key that unlocks the design of everything from the tiniest bearings to the most massive industrial turbines. So let's bring all this back home. This isn't just some abstract theory in a textbook. This invisible force is at work all around you, every single day. This is the principle that allows the parts in your car's engine to survive spinning at insane speeds. It's what allows those huge power plant turbines to spin almost without any friction to give us electricity. It's even at work inside a computer hard drive. That read/write head is literally floating on an unbelievably thin cushion of air. It's a perfect example of the same idea, just with air instead of oil. This invisible force is just everywhere. So the next time you turn the key in your car, or flip on a light switch, or even save a file on your computer, you can think about that tiny, powerful wedge of fluid doing its invisible work. It really makes you wonder, doesn't it? What other invisible forces, what other little bits of elegant physics are hiding in plain sight, quietly making our entire world possible?